I'd like to welcome you to this lecture sponsored by the Michigan Memorial Phoenix Project and the Nuclear Engineering and Radiological Sciences Department at the University of Michigan. Before I introduce our speaker, I'd like to say a few words about the Michigan Memorial Phoenix Project. The University of Michigan Regents resolved in 1948 that the University of Michigan create a War Memorial Center to explore the ways and means by which the potentialities of atomic energy may become a beneficent influence in the life of man, to be known as the Phoenix Project of the University of Michigan. Therefore, the Michigan Memorial Phoenix Project and this lecture represent a living memorial to the men and women of the University of Michigan who gave their lives in the service of this country in World War II. Our speaker brought to my attention that he is in fact a survivor of World War II, and as a child he spent time in bomb shelters in Budapest, Hungary. So this is particularly appropriate that he should be giving this lecture. And the topic of his lecture, Worldwide Progress Towards Realizing Nuclear Fusion Energy, is also very relevant to the goals of the Michigan Memorial Phoenix Project concerning peaceful uses of nuclear energy. Now a few words about our speaker. Professor Miklos Porkolab is an internationally recognized physicist known for his work in both experimental and theoretical plasma physics. Since 1995, he's been director of the MIT's Plasma Science and Fusion Center and head of its Physics Research Division. He graduated from the University of British Columbia in engineering physics in 1963 and obtained his Ph.D. in applied physics at Stanford University in 1967. While at Princeton University in the early 1990s, Dr. Porkolab carried out pioneering experimental and theoretical research in the area of nonlinear wave-wave and wave-particle interactions and parametric instabilities. His current research interests include advanced Tokamak physics research through heating and current profile with RF waves, and a study of turbulence and transport in Tokamaks. Dr. Porkolab is a fellow of the American Physical Society and the American Association for the Advancement of Science. His recent awards include the Károly Simony Memorial Plaque and Prize from the Hungarian Nuclear Society, the James Clerk Maxwell Prize from the American Physical Society, which is the highest award of the American Physical Society Division of Plasma Physics from 2009, and the Distinguished Career Award of the Fusion Power Associates of the United States in 2010. So please join me in welcoming Professor Miklos Porkolab.
Well, thank you very much, Ron, for the nice introduction and also for inviting me to here to give this colloquium. I'm extremely pleased, and I really enjoyed visiting the laboratories today earlier and talked to the many students here, and so I thought that maybe I will give a general overview talk of fusion and start from the basics for those of you who may not be experts in the field, then get to increasing complexity and talk a little bit about present physics research topics and issues that are critical toward making ITER a success. ITER is the International Tokamak experimental reactor being built in Europe by 7 partners in the world, including Europe, who is paying 45% of the total cost, and 6 other partners, including the US, China, Korea, Japan, India, and Russia, each paying 1/9 of the total cost, which in year 2000 was estimated around $4.5 billion, and now its present estimate is up toward $20 billion. So it's indeed an extremely expensive project, maybe the largest scientific project worldwide that the world tried to do together. So it's an experiment also in how we can collaborate in big science in the future. And I'll show a number of pictures about ITER. I also want to acknowledge the many contributions from different colleagues I collected from around the world, slides which I thought would make help to complete the picture, and I got permission from them to use their slides. So I have on each slide the name that I got the slide from. So just to give an outline, I thought that I will start with just introducing the very basic what a fusion reaction is, why it's attractive environmentally, then get into how we confine hot plasma, which is the medium in which fusion is achieved, and then look at past experimental results and scaling up to what we call an ignited plasma regime, which is a self-heated plasma from nuclear reactions. And we actually don't need that for a working reactor. We probably, that means that the gain is infinite. We need some gain like a factor of 30 compared to the heating power, so we can control the plasma. I'll get into that in a little bit. And then I will talk about ITER, what it looks like and what it's trying to do. And then get into some physics issues, which I call supporting R&D. This is the ongoing experimental and theoretical research program going on worldwide. And I can only talk about a few of the issues because of time limitation. And then I have a few slides showing what our different plans for different countries are for future going beyond ITER, which is an experiment, going toward a demo, which is a demonstration reactor, and ultimately leading to a commercial reactor. And then I will give a brief summary. So that's the outline. So the fusion reaction, the most probable one is the fusing of a deuterium and tritium nucleus. And the deuterium consists of a proton and one neutron, and the tritium has two neutrons. So these are elements of heavy water. In the fusion reaction, at high speeds, they collide, fuse, and turn into a helium ion, and that's called alpha particle, and that has two protons and two neutrons, and then a fast neutron is emitted. Now, in this process, you have an energy multiplication of 450 to 1. And so what happens is by E equals mc squared, a little bit of mass disappears, and it converts into these two very energetic kinetic energy of the particles. And so typically the initial energies of the deuterium and tritium correspond to a temperature of something like 20 keV. I'll get back to that. We measure temperatures in electron volts or kilo electron volt. And it gets magnified into an alpha particle, which is 3.5 million electron volt, and a fast neutron, which is about 14 million electron volt. So we started with 20 keV, and we go to MeV particles. So this is the energy multiplication because of converting mass to energy. The alpha particles, then, these are positively charged helium nuclei. They are confined in a magnetic field in the plasma, and they keep colliding with the background plasma. And so they maintain heating the initial gas, ionized gas, and maintaining its temperature. So we can remove the initial heating match, if you like, because it's self-sustaining ultimately, if we can keep the heat long enough together. And the fast neutron carries the energy away, and it goes in a blanket which has lithium in it, and there's a nuclear reaction which produces tritium. So that's the other element that we need here as a fuel. So if you like, the raw fuel is the water from which we get deuterium, and lithium from which we make the tritium. And the rest of it goes into a thermal cycle, which I will just show systematically. Now, in order to do this efficiently, we do this in a plasma because the temperatures are millions of degrees, hundreds of millions of degrees of the gas. So the gas becomes an ionized gas, which we call a plasma, so the electrons and ions move independently. And of course, this is an electrically responsive gas or fluid, so it responds to electric and magnetic fields. There are boundaries which have gradients that generate instabilities and fluctuations, and so it becomes a rather complex medium to understand. And so that has a lot to do with trying to understand the turbulence that develops in this kind of plasma, which then ultimately dominates transport of heat out of the plasma rather than collisions. And I will just refer to that briefly later on. Now, plasma is all over the universe. 99% of the visible universe is in the plasma state. And so there's a diagram showing the variety of temperatures and number density of particles. And I just want to point out that the fusion reactor conditions are here about 10 to 8 degrees Kelvin, or 100 million degrees Kelvin. And we measure that usually in electron volts. So 1 electron volt is 10,000 Kelvin. So 100 million Kelvin is 10,000 electron volt, or we just say 10 keV. Okay, so that's a typical fusing temperature in maybe 20 to 30 keV. And we have already achieved 20 years ago temperatures of the order of 40 to 50 keV. So to get the temperature at 4 to 500 million degrees was already done 20 years ago in both in the TFTR, the Tokamak fusion test reactor in Princeton, and also in JET, the Joint European Torus. The issue is at what density you get that. And so the densities that we need are of the order of 10 to the 20th particles per cubic meter. You can't really read this with the log scale, 10 to the 20th. And the densities that where these temperatures were achieved in TFTR, they were somewhat lower, maybe a factor of 2 lower. And also the heat was not contained long enough, and that has to do with this energy confinement time. But I'll come back later how to characterize that. So then the idea of how a fusion power system works is that you have a hot fusing plasma, which initially you heat with, say, radio frequency waves or energetic ion beams. Once the temperature goes up, then it begins to fuse, begins to produce the alpha particles, which then are caught by the plasma and keep heating the plasma, and then the neutrons go out to this wall, which has lithium in it, which makes a tritium, and you feed that back. So you get your two fuels, deuterium you get out of seawater, basically. And ultimately, you have a blanket, which then goes through a heat exchanger, just like any other reactor in the turbine, and you generate electricity. So that's sort of the idea. So the only issue is how this plasma furnace in the core of the typical reactor system works, and how efficient is it, and there are many engineering details. So just to get a little bit of feeling of how much energy you gain, it's interesting to compare a fusion reactor and a fuel versus conventional fuels. So the energy contained, for example, 40 tons of coal is equivalent to 1 bathtub full of water that you get a deuterium out, that's 45 liters, plus the lithium that you have in a lithium-ion battery in a 1 laptop battery. That's the equivalent energy. So this would generate about 200,000 kilowatt hours of electricity. So it's an interesting thing to realize that. This is why people are looking at fusion, because it's so attractive. Again, in the water, you have 1 out of 6,700 atoms deuterium, and the tritium is made in a blanket. Another interesting picture I saw recently was from Mickey Wade from General Atomics. It's missing the name at the bottom. Again, if you want to generate 1 gigawatt of power, so this is a large power reactor, 1,000 megawatts in 1 day. If you use coal in a coal plant, you need 18 million pounds of coal, which is 80 railroad cars like this. The equivalent amount of energy that you get in a fusion plant is 1 pound of deuterium and 1.5 pounds of tritium. Produces the same amount of energy. And if you look at the waste that's produced, that's really interesting. I didn't look at these numbers before. 60 million pounds of CO2, 1.2 million pounds of sulfur dioxide, and 160,000 pounds of nitrous oxide, and fills 8,000 of these big containers. Whereas from fusion, you get 2 pounds of helium as the product, because ultimately the helium ions slow down on the background plasma and they slowly diffuse out and neutralize at the edge of the plasma. And so you collect helium gas as the ash, if you like, and it fills 400 balloons. So this is really interesting why environmentally it's so much more attractive if you could make a fusion reactor work. And so here's a number of, I'm listing attractive features: abundant fuel available to all nations, no carbon emissions, short-lived radioactivity, I'll come back to that, can blow up, resistant to terrorist attack, less than 5 minutes of fuel in the chamber, low risk of materials proliferation, no fissile materials required, compact relative to solar, wind, and biomass, and not subject to short-term or regional weather variation like solar, and no large-scale energy storage, and so forth. So the real issue is, can you develop this, and what is the cost of electricity? Because ultimately, it has to be competitive. Now, there have been some reactor studies, the so-called ARIES studies, which showed that after like 100 of a kind, it's going to be a similar cost to fission. That remains to be seen, given that ITER cost is now up to $20 billion, even if it's a first of a kind, and it doesn't have many of the technologies that you're going to read in a fusion reactor, like tritium breeding and so forth, blankets and materials development. In my mind, it's still, I begin to question this. And we're talking about this in our community. But anyway, the early estimates showed this. So it remains to be seen yet. Now, the radioactive waste is shown here. There's one diagram from Rob Goldstone, and you can see these are years, 10,000 years. This is years when you decay away the radioactivity down to the coal ash regulatory level. So below this, you have no concern. Above that, you have different kind of burials. So if a fusion reactor chamber is made of reduced activation ferritic steel, which is the European like this, then it would take about 100 years burial to decay away to a reasonable level. When you look at vanadium alloys, then you can make fusion decay away within 20 years so that it's not radioactive anymore. And the technology for this needs to be developed. You can make little pieces of vanadium, but to do big engineering pieces, we don't have it in hand. So there's going to be a major engineering effort ultimately, once we show that the physics works, to make a fusion reactor that is really attractive environmentally. Right now, this ITER is going to be made of stainless steel, and so it's going to be ultimately a big chunk of radioactive material. But the future is going to need this development. And silicon carbide composite, it's even lower activation. So there's some attractive features of the radioactive waste. Sometimes I'm showing this up front because these questions often come up at the end of talk. So, all right, so how do we confine plasma to do the fusion in? Well, the sun does it by gravitational forces, which is very easy because it's huge. And in the laboratory, this gives sort of an example of how you might do it in inertial confinement fusion. So this is the basic concept behind the National Ignition Facility, where they use enormous lasers to compress little pellets of fuel, and rather complicated design, actually, holograms and so forth. I will not be able to talk about this, but it is a very interesting concept scientifically, and the laser system is working. The plasma physics is giving problems right now to achieve ignition. And of course, on the surface of the sun, we see these enormous solar flares and prominences, which gives an idea how magnetic fields might confine plasmas. And so to get into a little more technical discussion of this, so we confined charged particles in magnetic fields. And of course, in magnetic fields, electrons and ions are gyrating around field lines with finite orbits, which is described as perpendicular velocity divided by the angular frequency, which is just depends on the magnetic field and the charge. So the stronger the magnetic field, the smaller this Larmor radius or gyro radius of the particles. And so Of course, in a straight line configuration, the particles would just stream out along the magnetic field line. So you have to do something with that. So the simplest idea is to wind this into a torus, in a donut-shaped torus, so that the magnetic field lines go around and come back, and go around and come back, and then the hot plasma is in there. And you can do this by putting pancake magnets around this donut, as shown here. And so in principle, this would be a relatively simple concept to confine the plasma. There's only one problem with this idea, this simple idea of a simple torus, and namely that when you look at the coils, you see that there's more current density inside the torus than the outside in these pancakes. And that means that you generate a stronger magnetic field on the inside than on the outside. And if you look at mathematically, this toroidal magnetic field, as we call, it falls off radially as 1 over the major radius of the device. So 1 over the major radius of the donut. And so that means that the field strength is weaker on the outside than on the inside. And so if you look at this relationship, the gyro radius is proportional to V perp over B. And the theory said, which I can't get into it here, that the magnetic moment is conserved, which means that the perpendicular velocity is going to be constant. And so the magnetic field is falling off. So this gyro radius is changing from the inside to the outside. And the consequence of that one is that the orbits are producing a net drift of the electrons and ions. And one of them will drift upward. The other one drifts downward, depending on the direction of the magnetic field. And so this doesn't hold the charged particles together, only for a short time until they drift up and down. And once you separate the charges, you set up a vertical electric field. And once you have a vertical electric field, which is perpendicular to this magnetic field, then what do you get? You go back to your basic elementary E&M course and you find, oh, well, I get an E cross B drift. And the E cross B drift is independent of the sign of the charge. So once you set up this electric field, then that's in the vertical direction, toroidal direction, magnetic field. The E cross B drift is radially outward. And so you eject the plasma, electrons and ions together, because it's independent of the sign. So this confinement scheme, while it's very nice, it needs something to be done to it. So people have, in the early days, recognized this. So what you do is, one thing you can do is you can induce a current in the plasma. And that's the basic idea behind the so-called Tokamak concept that the Russians invented. So you put in an ohmic transformer primary. You can do it in the center here. And the plasma forms the secondary. And so you induce a magnetic flux which drives a current in the plasma. So the plasma electrons then drift. And typical currents that we drive in today's machines are of the order of 1 million amperes, 1 to 2 megamps. In the early days, we drove a few hundred kiloamps. And that current then generates its own magnetic field. So you create a poloidal magnetic field, namely a magnetic field that goes around the current. And so now you have a total net magnetic field, which is a combination of the toroidal and the poloidal field. And this poloidal field typically is 1/10 of the toroidal field. So the result is that the magnetic field lines spiral around this torus. They go from the outside to the inside to the outside inside. And the result is that the charged particles move from the outside to the inside to the outside. So you average out this bad orbit, and basically you can create a sort of a magnetic surface, if you like, which then confines the plasma. So the plasma stays together. You short out this electric field that would arise. All right, so this is the concept behind the tokamak. Another concept is the stellarator, where instead of this, you do very complex magnetic fields twisting around, which produce a plasma shaped like this. I didn't show the coils here. And that has essentially the same kind of idea and shorts out the electric field. This stellarator idea was invented by Lyman Spitzer in the United States, at least. I'm sure the early Soviet theorists also thought of that. And so the story is a little anecdote that he invented this idea of riding up on chair number 1 in Aspen in the 60s when he was a skier. And I don't know how many of you have skied at Aspen, but it was a small chair going up the mountain. I think it was only a single chair and maybe a double. I can't remember. I went up on that chair. It's been replaced by a modern chair. So sometimes it's good to get away and think about difficult problems, and an idea might come to you, just like that. Anyway, most of the world's machines follow this Tokamak concept, and of course one of the issues is that this is not a steady state because you have to induce this electric field. So the typical pulse lengths are a few seconds. In today's machines, maybe 10 or 20 seconds in the biggest ones. And in ether, it'll go up to 400 seconds, because it's a very large machine you can put in a very big transformer. But ultimately, to go to steady state, you will need something else. You're going to have to drive currents with RF waves or energetic ion beams. And it turns out that once the plasma pressure is high enough, it generates its own current, called the bootstrap current. And so that we call an advanced tokamak, a case that operates at high pressure, has lots of bootstrap current, and a little bit of auxiliary current to make it steady state. So these are some of the concepts and some of the issues. And so here's a collection of different machines around the world inside that pursuing both the tokamak and the stellarator concept. So the world's largest tokamak now is the Joint European Torus, and you see this is a 3-meter major radius machine. There's a person working in there. And you see wave launchers, RF wave launchers, and so-called Faraday shields rods across it to protect it from the plasma. And then you see all these tiles inside. Typically, these were carbon tiles, and now they have been replacing them with tungsten. And the General Atomic tokamak is shown here, D3D. That's our largest tokamak in the US. And a spherical tokamak, which was the middle picture, is shown here in Princeton. And our smallest tokamak is Alcatraz CMOD, is shown here inside. You see the RF launchers, and it looks very big. But actually, this machine is only 1/5 of the size of this jet. It's just blown up. A very creative photography. But we have 7,000 molybdenum tiles on that. And that's important because we finally got to prevent tritium retention in the carbon. Ultimately, we think we need to go to metallic walls and tiles. And right now, we're exploring tungsten for that. And molybdenum is very similar. So actually, we have had a lot of experience on CMOD with that. Now, there are 2 major new tokamaks, actually 3 in Asia. They're billion-dollar class machines. They're superconducting magnets running around 3 Tesla. And the K-Star is in Korea. East is in China. They're both comparable size, about 1.7, 1.8 meter major radius. And actually, this K-Star was originally designed in the US. This was called a TPX, Tokamak Physics Experiment, that we designed in the 90s at Princeton, but we couldn't get money to build it. So we gave it to the Koreans, the design, and they modified it somewhat, and they built it. So if you ever go there, you see a big sign on the Hyundai. And so some of us feel bitter about that when we go to visit there. We did a lot of the original design, but we couldn't get the money from Congress to build it. And Japan is building a superconducting machine together with Europe, which should start up in 3 years, called the JT60 Super Upgrade, or Super Advanced, I think. And then there's a couple of stellarators here. One is running in Japan for a number of years. It's superconducting magnets also. And Germany is just finishing maybe another year, the Wendelstein 7X superconducting stellarator. And that's sort of a most advanced stellarator design. So we'll see how it works. So there are many experiments going on worldwide. This is just summarizes. There's also another smaller superconducting machine in India that they built, just turning it on now. So let me just move on. So the rest of the world, I mean, Asia is really growing. Japan, Korea, China with billion-dollar class machines, and India even for several $100 million machine. So they're moving ahead. Now the progress in fusion power has been actually impressive in the early days in spite of everything else. And what we found that building larger and larger machines, the fusion power grew until TFTR and JET running with deuterium and tritium was producing around 10 megawatts of fusion power for a second or so by the mid-90s. And after that, we did not build, then we decided it's ready to move on to the next machine, and it became at least twice as big as this and very expensive. So the world decided to join together and build this ITER. And after a lot of negotiations and arguing and complicated politics between Japan and Europe, it was decided to build it in Europe, in France, in Cadarache, and in return, the Europeans put in something like $500 million toward building this new Tokamak in Japan. But as a result, the Europeans putting up 45% of the cost of this machine. So that was the basis. So there was empirical growth and basis for going ahead with the next major device. I thought it might be interesting or worthwhile to look at how we assess the gain in a fusion reactor. So one could define the goodness factor as a fraction of alpha particles in a fusing plasma. I would say is the measure of the fusion energy gain. And so if you look at the reaction, deuterium and tritium producing a helium 3.5 MeV, a neutron 14 MeV, so it's a total of 17.6 MeV. And if you define the fusion gain as a fusion power divided by the heating power you have to put in initially to produce this 20 keV plasma, then the total fusion power is 1 plus 4, 5 times the helium energy. So it's 5 times P alpha, or the alpha particle power. And if I look at the alpha heating fraction, it's P alpha over P total, which is heat plus the alpha. And so if I convert this back to this Q, then it turns out to be Q over Q plus 5. Okay, so this is the gain divided by gain plus 5. So if you look at what the gain is, so break even is considered as gain of 1. So you produce as much fusion power as the heating power you put in. And so in these early experiments, they had a gain of approaching 1, not quite 1. In that case, the alpha heating fraction is only 17%. ITER is designed for a gain of 10. So there the alpha heating fraction is 66%. For a reactor, you need more power produced from fusion, so you need a factor of gain of 20 to 30. And so that will produce 80 to 90% alpha power. And ignition would be an infinite gain. You can turn off completely the heating power, but we really don't desire that because you need some power to control the plasma and perhaps heat at different places or drive current to make it steady state. So that's you need less gain for that. Okay, so here's a picture of the fusion power produced in TFTR in 94. So this is in megawatts. JET in 97. 16 megawatts, but it was only a gain of 65% because they needed close to 25 megawatts of heating power to produce this. And the same in TFTR. And if you went to longer pulse in JET, it had a gain of 0.2 only, but that lasted like 5 seconds. Now, if you keep in mind these time scales and the fusion power, then we'll come back to that and show what ITER is going to produce. So maybe I can show that now and come back. So ITER is designed to have a fusion power for about 500 seconds of close to 500 megawatts. This is a result of a simulation based on the latest codes. And 15 megamps of current and auxiliary power of about 50 megawatts net power, or about 75 megawatt source power. So if you look on this picture where the earlier fusion power production was, it's in this little yellow square at the beginning. That's all it was, it's a blip. So the fusion power is only 10 megawatts and only for a second or so. So it's interesting to know, this is the challenge. How do you produce a plasma and maintain it and control it? And if you think how much effort it took to make JET and TFTR work, then it gives you some idea of the challenge that's facing us. Okay, let me just go back now and look at, again, this gain. So the fusion performance increased with size, and that has to do with the confining the energy. And so when you look at physics, this fusion gain is characterized by the fusion triple product, as we call it, the density of the ions, the temperature of the ions, and the confinement time, energy replacement time, how long it takes for the heat to diffuse out. And so it's the product of these three that really determines the gain. And what you find is when you plot this over years and go to larger and larger machines, that this fusion gain has been growing with machine size. And here's the ion temperature. And so here is the near break-even results of JET and TFTR up here on this curve. It turns out this yellow regime is where the ion temperature is higher than the electron temperature, Ti bigger than Te. And it turns out that the confinement of ions is better than electrons. So in many cases, the ion temperature was higher than the electron temperature, and it determined the ion temperature that you will get. But if you go in a larger reactor type plasma like ITER, electrons and ions will equilibrate. The equilibration time is shorter than the total energy confinement time. And then you have a little more stringent condition. And so here we are with the best machine performance, and we have to get up to here either, maybe a factor of 4 in this parameter. So here's, we need, actually for ignition, we need up to factor of 4 up to here, but in ITER, we're trying to go up to a gain of 10. And while this looks like not very far away, it is a challenge to get there, and the question is, will the physics change? So here is a progression of confinement time in seconds versus some scaling law. It's like wind tunnel experiments that were concluded from a whole bunch of experiments in the past. They go in a progression like that. And so the largest machines had a confinement time of about 1 second. And this was JET, the circles. And the question is, for ITER, we'll need something like 4.5 second confinement time. And one of the questions is this progression going to keep going up? Or will something go wrong? Or when we switch from mostly ion heating to electron heating, will this curve turn around? So ITER is still an experiment to achieve its goal of a gain of 10 and the temperatures that we need to achieve and the confinement time. So while this looks a small extrapolation, the physics could change. And so this is one of the main reasons why we're doing this experiment. The other one is that alpha heating is going to replace, most of these machines were auxiliary heated. As I showed, the alpha fraction was only like 17% at most. When you go to 66%, the alpha particles are 3.5 MeV particles. They can drive turbulence. They can drive instabilities and various kind of alpha instabilities. So we have to test those. Even if they occur, are they dangerous? Are they going to throw out the alpha particles? So there's a lot of studies and experiments going on and computer simulation, how the alpha is going to behave. So these two things are, in my mind, the critical issues that ITER will have to address, even though it's not going to test reactor technology. So this is a big machine. And is a cross-section of it, what it's going to look like. And there's a person standing here. I don't know if you can see it from the back. So this is a 6.2 meter major radius. and 2-meter minor radius, and vertically 3.5-meter radius. So this is a very big object, and the scale is enormous. The engineering complexity is enormous. And so I have a few other pictures. I'm going to buzz through this quickly. They sort of, this is an artist's conception of what the whole plant is going to look like, where the core is in here. This is a design drawing from the US ITER organization. This logo is the US ITER organization. I got this from them. So you see it's a rather, again, complex thing. And here's a description of what the US is doing for ITER. Who is doing what? So we are winding the central solenoid. The strand is actually made in Japan. And right now it's expected that General Atomics will wind this. We provide 8% of the toroidal field conductor. That's for the big coils. We provide a pellet injector to fuel the plasma and mitigate disruptions. Blanket shield design only, Oak Ridge. 100% of the Tokamak cooling water system. This is a big, expensive project, and so we do a lot of this. Kilometers and kilometers of water cooling. It's an enormous system, and water pumps and so forth. So it's not very interesting scientifically, but it was thought to be low risk, trying to reduce the potential budget overruns. Electrical network and so forth. Tokamak exhaust processing system. There is some RF heating system. Oak Ridge will do the ion cyclotron transmission lines and electron cyclotron transmission line. So the heating system is considered to be 20 megawatts of electron cyclotron heating, 20 megawatts of ion cyclotron heating, and perhaps 35 megawatts of neutral beam heating with 1 MeV ions, which is under development in Europe. So that's, nobody has produced more than about 400 keV ion beams in Japan after a number of years. So just the technology alone to make the MeV ion beams is a real challenge. And so I won't have time to talk about that. Now we are involved in diagnostics, so this is where some of the physics is going to come in. So when you want to do experiments on ITER, you got to build a diagnostic, or you will have to put in a proposal for runtime to do some physics experiments. So that's going to be done through diagnostics, and the diagnostics has been divided throughout the world, and there is a list of diagnostics that the US will build, and some of the institutional involvement is shown here. And again, I'll leave this list now. If any of you are interested in this, you should contact the appropriate people from different institutions that do that. Here's the pictures of what's happening in France. So they build up these enormous shock absorber systems for earthquake proof. If you have an earthquake, which is an earthquake zone, even Kadarash, it's not as bad as the original place that Japan proposed up at Rokasho, which is near earthquake zone that 9.5 earthquakes in the past 100 years. Anyway, they're building these enormous shock absorbers, and the whole machine and the floor will go on this to try to take it up a reasonably expected earthquake zone here. They finished the conference room. Here's the ITER consoles. They had the meeting in November. There's another building where, which is ready to wind the poloidal field coils. Fortunately, the poloidal field coils are not here yet. They're so big, you cannot transport it. You have to make it on site. So this is waiting for that delivery. And there's switch yards, and there's some office complex now ready where this central office is. But you see there's a lot more to do. The stuff is dug up and it's under construction. All right, so let me talk a little bit about some of the physics issues. And let's see, can I go on to 5 o'clock? Yeah. So there are a number of physics issues that need to be still studied and determine how to optimize the transport and so forth in this machine. So I listed some of these. I will not be able to talk about most of this except maybe transport and confinement. I will just pick one topic. These are, again, the Tokamaks worldwide that voluntarily studying these issues, and we have a coordinated effort now in the whole world, trying to look at individual topics and see if we can resolve remaining issues. So let me just talk a little bit about transport, which is what I spent most of my life on doing RF heating and profile control and AT studies. But when I was a grad student, I started with transport and studying drift instabilities in a little cesium plasma, just like you have here, little Q machine plasma, and watch how the instabilities grow from gradients and how they develop into turbulence. And then I tried to understand that, and I concluded that we had no codes, that the theory was too complicated, that I couldn't understand what's going on because it was strong turbulence. We had a weak turbulence theory developed, very rigorous. And we verified some aspects of that. But the world was very different than now. We have enormous codes that solve the nonlinear equations and simulate plasma turbulence. So now it's worth to go back and try to understand them. So the plasma shape is a complex, self-organized system. It isn't as simple as you think. So what happens is, and this is taken over from Jean Jacquinot, so I'm sorry about the original French science here. You see, I translated into English. And, but the original plasma pressure profile, which was mostly density profile or temperature profile, was simply parabolic like this. And it wasn't until we begin to, this is what you get if you produce an ohmic plasma. And then when you begin to heat it, as you increase the heating power, the plasma shape changes. And suddenly the plasma, instead of a green shape, suddenly jumps up. You develop what we call a pedestal at the edge. And then that pedestal holds up the internal plasma shape. The plasma shape may stay as the initial green, but it's all lifted up. So you end up with a higher pressure because the edge changes. It's almost like a Hoover Dam holding up the waters. Suddenly, if you hold it up, then you can maintain a high pressure. So this is called the edge transport barrier. And this confinement, the total energy confinement, is typically 2 times that of L mode. So L stands for low mode. H stands for high mode confinement. And this was discovered originally in the SDAX Tokamak in Germany around 1990, and Fritz Wagner was the leader of that program. And it wasn't well understood, or they suddenly saw this and published it. And it turns out it was also seen in Princeton in the PDX Tokamak, but they didn't think much of it, so they just ignored it. And then they went back to it after the German discovery and began to analyze their data, and they discovered, wow, yeah, there's something to this. And so in fact, if you had L mode confinement, either wouldn't work at all. So this is a self-organization. You're pouring in power and heat, and suddenly the plasma shape changes, and the pressure builds up this barrier out here. And so we're doing a lot of work trying to understand this, understand the transport in the core, and understand the barrier. Our theoretical description now is very good. We have very good codes to solve the turbulence equations in the core. The equations, particle orbits break down. The gyro radius is comparable to these gradients. You have sharp gradients. And we really don't have a first principles theory of this region. So much of the theoretical effort nowadays is concentrating in understanding what's happening here. And there's a lot of debates about that. And last week, for example, they had the so-called Sherwood meeting with all the plasma theorists. Go to different places. They went to Santa Fe and spent 3 days arguing about this. Whereas the transport people, where we compared experiment and theory in the core, we went to Santa Rosa 2 weeks ago. So we had our workshop there. So that was quite exciting. There we have a lot of code work comparing experiment and theory. So the situation is rather complex when you begin to heat the plasma. And near the edge, you can also have 2 sharp gradients, and MHD modes come in suddenly, called ALMS, edge localized modes. And you have to control those because they dump a lot of plasma energy out to the wall, like 20%. And because of the large energy content of this plasma, you can't tolerate it on the wall. So we need to mitigate that. Okay, so I mentioned this is sort of a more focused summary of the kind of regions that we study with coordinated research effort worldwide on different tokamaks, edge barrier. Another whole issue is the heat flux in the scrape-off layer. What's the impact on high Z, namely metallic walls, and the edge transients and so forth. So the different topics in physics that people are trying to study and understand, and we move from one topic to the other each year. This slide just shows some of the discoveries that if you look at the heat flux, very simply, it's characterized by the density times diffusivity times the gradient of temperature, and the confinement time is related to a squared, the minor radius squared divided by this chi. And it turns out that this chi is turbulent. So measurement showed if you calculate collisionally what the transport ought to be, what this diffusion coefficient ought to be, it's down here as a function of minor radius. This is from Torres Supra, it's a French superconductivity Tokamak. If you look at the ion diffusivity, it's higher. And if you look at the electron heat diffusivity, it's even higher. So this clearly shows that heat diffusivity is controlled by turbulence, not by collisions. If we had collisional transport only, we would have a fusion reactor probably 30 years ago of a meter size only. You can calculate how long. That would give you a confinement time of 4 or 5 seconds. But it isn't. That was, of course, the early hope, going way back in the early days when Edward Teller made some of these calculations. Wow, we can make a meter size machine. But so turbulence is the all-dominant factor in diffusion. And so we have an ongoing program in trying to understand turbulence. We have very large codes that simulate the turbulence now, solve the nonlinear equations. We have measurements with microwave scattering, laser scattering, electron cyclotron emission, where we actually measure the turbulent fields in the plasma, and we try to then compare them with experimental values of chi. And here is one nice result from a D3D tokamak, where you have the ion temperature profile, this solid line, and the experimental measurements predicted by the turbulent code at different regions with error bias, what the temperature should be. And then the turbulence was measured also. And here you again see very good agreement between measurements and the simulated diagnostic and the experiment. And so these turbulence, this is in the ion transport regime, which is due to turbulence driven by the ion temperature gradient in the plasma. We call them the ITG mode, ion temperature gradient mode. The electron transport is much less well understood, and it's higher than the ion transport, so we're still working on that. The other modes, so-called trapped electron modes, electron temperature gradient driven modes, and the nonlinear interaction of ITG modes also produce electron transport, so it's pretty complicated. So we are working on that, trying to understand this and compare with codes, which are actually extremely fascinating. The solutions of the nonlinear equation and toroidal geometry predict things like shear flows due to the radioelectric fields that are developed by the turbulence itself, leading to zonal flows and leading to higher confinement. The zonal flows tend to break up the turbulent eddies to shorter wavelength, reduce diffusion, and that may be the reason for the H mode. So there is a lot of interaction now between supercomputers studying turbulence and the experiment and understanding what's causing this turbulence and how we can control it, how we can break it up. Okay, I think the other topic is these ELMs, these edge localized modes that coming from here. And you see that when you exceed a certain pressure gradient, then you can create these oscillations at the edge, which dump plasma out. So we're trying to control this with by injecting pellets through the edge, and it begins to reduce the size of these so-called ELMs, or add additional coils outside the plasma that's beginning to break up the surfaces, so-called ergodization coils. And let me just go. Here's an example on D3D tokamak where they add these additional coils on the plasma, which then driven at sort of low frequencies and begin to break up the surfaces and yet still maintain good confinement. So here's what happens is it's called the I coil, put on magnetic perturbations, and as you raise the current, suddenly the elms disappear, and you have the quiescent plasma. And the confinement goes down a little bit, but you're still maintaining good confinement. This is just the heating power. It's a combination of neutral beam and electron cyclotron heating. So these coils are now adapted to ITER, and so these are kind of things that increase the cost. To build this coils, design and install it might add another $100 or $200 million. Okay, so and this just came up suddenly while the costs keep going up. As we're learning physics, we didn't know this physics. This physics coming out and we're building this machine, and suddenly we realize how we can fix the arms, and so what does it take? So it takes another $200 million. You can do it for $1 million on D3D, but when you put it on ITER, that's a different business. Anyway, these are the kind of things that we also are looking at modes that don't have elms. These are also recent discoveries. For example, the so-called I mode or improved mode on Alcatraz CMOD that we discovered that depending on where you put move the shape and the diverter region and change the shear, you can get improved confinement regimes from L mode, build up a temperature pedestal and no density pedestal, and so you get a better confinement. In the D3D tokamak, they discovered the so-called quiescent H modes, which produce strong rotational shear to stabilize these elms at the edge. But what you have is you find a smaller scale, low frequency turbulence that still cleanses the plasma. You need some instability to prevent the really steep build-up of the temperature gradient so the plasma goes unstable. So here the fine scale turbulence is doing that, which is at the edge, not in the core. So we're trying to understand that. Okay, the other whole issue is heat flux, and how you remove heat flux from the tiles. I think I'll skip that. The ideas of how to change the diverter, so-called snowflake diverter, that basically you're trying to increase the area of the footprint of the heat that's coming out from the plasma in the diverter region and spread it out on the surface so you have less heat flux per unit area. So people just developing these ideas. So it's maybe that in a reactor you're going to have to change the whole topology of the edge physics. And this is the kind of research that's ongoing, that's being discovered. And the theory is working on this. Okay, so I have a few slides, time is up, for the future. What do we need to do to go beyond ITER? And what are some of the ideas? So we've been working on this in the US fusion program, and we don't think we're ready to go to a demo after ITER. We think we need some step in between, and we used to call it the component test facility, which is mostly studying materials under intense neutron bombardment. So the present idea is that we could build a more modest experiment called the Fusion Nuclear Science Facility, FNSF. This is a low gain machine. It might have a Q of 2 or 3, but it's steady state. And it's running at high density, so you have a big neutron flux, and you can study materials with it. And so there are different designs. Some of these are copper machines, not even superconducting. At Oak Ridge, at General Atomics, and Princeton has some more ambitious idea to try to actually produce some samples of electricity with a blanket piece near the edge. And whether, again, this may be a $2 to $3 billion class machine. I'm just guessing what it is. If it's a 3-meter machine, it's the size of jet, but it's running steady state and high current, and it's got blankets and so forth in it. So there's some of the functions of a blanket design. Again, there's a whole technology that will need to be solved, and in my estimation, it's going to be just as difficult as the plasma physics and expensive. And finally, there's a few cartoons of development path of fusion in Europe. They relying on international collaboration to try to gain more physics, and rely on ITER. And they think that after ITER, they may be able to go to a demo called a large nuclear machine and start construction in 2030. And maybe even produce some electricity. And so fusion electricity in the mid-40s. So you see it as 30 years from now. And you've heard it's always 30 years from now. But you can appreciate the problem that if we go in serial steps, not in parallel roads. We should have an intensive materials development program now. We should be building an FNSF now. In 10 years, we could build it and have really a major nuclear materials test facility for blankets and walls and so forth. And what does it take to develop new alloys that take 14 MeV neutron bombardment? We don't have those. Here's the Chinese fusion energy development path that they presented. And again, they have East. These are the two Chinese machines. The East is the new one, superconducting, and they would rely on JET also, and ITER, and feed into Chinese fusion engineering test reactors, CFTR, somewhere around 2030 to 20, well, let's see, no, this is between, I don't know how to read this, 20 to 25 here and 2030. So maybe near the 2020s. So this needs to be started fairly soon. And then that would go into, so this is like our FNSF. And would go into a demo on 2040, and then a fusion power plant, I don't know, 2050, 2060. This is sort of the time scale that you're really talking about when you say, okay, when we'll have fusion power, you know, by that, the average person means, okay, give me a gigawatt of electricity or 100 megawatt into my line. It isn't that you have a research reactor which you're trying to figure out problems. And this is the Korean plan. I won't go through this. There's similar timelines. So let me just summarize. So I think fusion is an attractive energy source. And I had one diagram which I removed that if you could produce fusion power by 2050 and beyond, large scale, it would actually contribute to the world's energy program and provide clean energy and penetrate the energy market on a reasonable time scale. It assumes that before that, we're going to have fission. You should be happy that the Chinese are building, I think they have like 30 reactors on design, what I saw in the newspapers. They realize, you know, they need 30 gigawatts. They need enormous amount of power to clean up the air. They're basically suffocating. I don't know if you've ever been to China. I've been there several times. And like I went to Xi'an in the fall, and the sun never rose. In fact, it looked like it was dusk all the time, and the car lights were on all the time because you couldn't really see very well. And there was just no air. If you didn't stay in a air-conditioned room, you were actually coughing and suffocating. I mean, it's terrible. And apparently that lasts for 2 or 3 months in the fall. So we're moving ahead with international collaboration. This is an expensive activity. And but I didn't have time to go through. There are many physics issues. I just try to tell you a few of them that will need to be solved and resolved. And we need many experiments, so that our domestic program has to be maintained. It isn't just that, well, I found today on one shot, I found a really great regime. You know, the operation has to be robust. When you go to a reactor, it has to operate day in, day out for 2 or 3 weeks, and it can have disruptions and blurs, so it destroys the machine. So there's a big difference between doing an experiment in a lab and once in a month see some nice operation versus a robust, continuous, reliable operation when you're talking about a $10, $20 billion device that could be destroyed. So that's why I feel we need that. And then the materials and advanced technology research is going to have to be pursued. demounting superconducting magnets for maintenance would change the whole scheme here, and you need high temperature superconductors to do that. Okay, one of the issues is how you replace components if you can't take the machine apart. You know, downtime is really unacceptable. So I think that that's going to have to be developed. And finally, fusion is a long-range R&D program, and education has to be an essential part. You guys when you're gonna be my age, hopefully you will have seen a Q of 10 or years. It's just a long range, and to have reactor solutions materials, this is going to take decades more. And so it's critical that the next generation keep coming to this work. So I'd like to finish with that. Thank you.